Okay, next we're going to hear from Whitham Reeve about the observations of ultra-low frequency waves at Anchorage, Alaska. And go ahead, Whit.
Okay, so I want to talk about ultra-low frequency waves that I've observed in Anchorage with the magnetometer. Certainly, we're not talking gigaparsec distances. The magnetometer is on the ground. So I'm observing what is caused by the solar wind. So we're still in the solar system for this presentation. I just have some introduction remarks, talk about what ULF waves are, how they're classified, a little bit about the observatory and the instrumentation that I'm using. And then I've got a whole bunch of observations that I've taken over the last solar cycle and at the beginning of the current solar cycle, and then some discussion. So what are we doing here? We know that the solar wind causes a lot of really interesting geomagnetic phenomena that are recorded by ground magnetometers. And among these are ULF waves, or ultra-low frequency waves, and that's a modern name given to periodic variations in Earth's field observed on the ground. Now, this phenomena has been called a bunch of different names over the years, including micropulsations and magnetic pulsations. And when I first got interested in this, and this is over a decade ago, I read about micropulsations and I observed them on my magnetometer. But when I did searching for papers that would describe micropulsations, I came up against a brick wall in about 1960 or 1961. I couldn't find any papers after that. And it was because the terminology had changed. By changing my search to ULF waves, now I started getting things that were much more current. So what are ULF waves? Well, they have frequencies of a few millihertz to a few hertz by definition, and which corresponds to periods of several minutes to fractions of a second. And the wavelengths are comparable to the scale size of the magnetosphere, which is quite large. And they play a fundamental role in transporting energy throughout the geospace system, which includes the Earth and its magnetosphere. And the science part of it is that the scientists investigate ULF waves to get information about the magnetosphere's particle density and structure. And it turns out that having ground magnetometers is a good way to measure in parts of the magnetosphere that are hard to directly measure. In other words, we can't get to it either because it's too low for satellites or too high for balloons and rockets and things like that. So the ultimate goal, though, is a better understanding of space weather and its effects on Earth and technology. And of course, space weather is one of the topics that I spend a lot of time with in my own amateur observations. This is kind of a standard image that shows the effects of space weather. It affects satellites, airline operations, particularly over the poles, ground instrumentation, power systems, pipelines, things like that. So space weather is a really important topic these days, has been for at least a decade that I've been involved in it. And so ULF waves kind of figure in those types of studies. Now, this magnetogram, this shows the variation in a three-axis magnetometer here in Anchorage, about 50 meters away from where I'm sitting right now. And this is a 24-hour time scale. on the bottom horizontal scale, and then the change in magnetic flux density is shown on the vertical scale. And this was back in 2010, and is one of the early magnetograms where I started to see ULF waves. Now, I didn't know at the time what they were called. I just called them noisy periods. But you can see that the magnetic field is tooling along here, and it's pretty quiet up until about 1500, or certainly at about 1730 UTC. And you see these rapid variations here in the magnetic field. And I just call that, I called it magnetic noise. I didn't know what caused them, but now I realize that they are called ULF waves. So that's a very early observation for me of that phenomenon. So ULF waves are generated in the magnetosphere. They're not generated outside by the solar wind. They are certainly instigated by the solar wind. And the magnetosphere is the region of space that's dominated by Earth's magnetic field. And this image here shows kind of a schematic, I guess, of the magnetosphere and the outside the magnetosphere. And so the magnetosphere is this cavity over here on the right-hand side of this image. And we have an important component of how it's affected is the bow shock from the solar wind, which is this white diffuse line here. And then we have the magnetosheath, which is over here on just to the right of the bow shock. And it's a turbulent region in which charged particle flows are heavily influenced by the solar wind. So that's the magnetosheath. And then we have the magnetopause that's right below that, or right inside of that. And that's where the Earth's magnetic field is balanced by the interplanetary magnetic field that's coming from the sun. And then also inside here, around the radiation belts, or near the radiation belts, is the plasma sphere. And the reason I bring all of these up is because every one of these has an effect on ULF waves, and that I'm measuring on the surface. Now, we know that electrons and ions are charged particles, and they're everywhere in the magnetosphere. They have a continuous and very wide range of energies. They're everywhere, but the energy levels of the plasma varies throughout the magnetosphere, and those different locations called the plasma sphere and so on. Now, the movement of these particles is constitute an electric current, and these currents then couple the separate regions of the magnetosphere. So this drawing here is kind of a three-dimensional, shows the magnetosphere cavity in this kind of a blue area. And then if you look closely, you can see field line currents, ring currents, cross-tail currents. We have night side magnetopause currents. All of these currents are looped. In other words, they don't begin and end at infinity. They actually loop around within the magnetosphere. And ULF waves are then generated by the interaction of the currents with the plasma and the magnetic field. And some of the maybe the most familiar currents that are flowing in the magnetosphere are the equatorial ring currents. Those have been known about for quite some time. Auroral electrojets are current systems at northern or at high latitudes, not far to the north of Anchorage. Those currents are flowing all the time. And then we have the magnetic field aligned currents. And these are currents that basically flow along Earth's magnetic field lines. Now, the magnetosphere also has electric fields in it. And so we have not only the magnetic field, we have electric fields, and all of these interact then to produce ULF waves. Here's kind of a breakdown of the three kind of basic types of ULF waves that are known about. Now we have the field line resonance, and that is shown by the blue oval over here. These are magnetic field lines that surround Earth, and these get jiggled back and forth. And when you have a moving magnetic field or a changing magnetic field, then you have currents that are associated with that. And if you're accelerating electrons, then you have emissions from those electrons. There's also the waveguide or cavity mode, and that's shown by the red squiggly lines here. And these are produced mostly on the day side of the Earth. So in other words, it's illuminated. It's the part of the magnetosphere that's illuminated by the sun. And then there's the wind over water waves, the KelvinHelmholtz waves, or KelvinHelmholtz instabilities. And this is caused by the flow of the solar wind around the magnetosphere. And this produces surface waves that are able to emit radiation or electromagnetic radiation. And this is analogous to wind over water or wind over the ocean or a lake or something like that. So this is just another schematic representation. The field line resonance that I spoke about earlier is the jiggling of the Earth's magnetic field lines, and they can either jiggle left or right as shown on this view here, or they can contract and expand. And both of those are movements in or a change in the magnetic field. And so we can have generate electromagnetic waves from that. We have cavity mode, which are a different phenomena. So this would be the magnetic field line shown in thick red line around here. And then we have the cavity modes that are producing the ULF waves shown inside of that. And then over here is a simulation that NASA had done that shows the solar wind coming from the right. And here you can see the bow shock here on the right-hand side. And then these waves are the wind over water analogy for the KelvinHelmholtz waves. Now, these are ULF waves are classified according to the scale that's shown here. They're broken into continuous and irregular pulsations, PC and PI. And then they are further broken down according to the frequency range or similarly the period. So we can see that the PC1 covered the range of, for example, 200 to 500 millihertz. So the 5,000 millihertz would be equivalent to 5 hertz. And then they go down in frequency from there to PC5, or continuous pulsations classified as 5. And now we're only talking like 1.7 to 6.7 millihertz. So these are, this is why they're called ultra low frequency. Now, these are electromagnetic waves, but the magnetometer that I have only measures the magnetic component of that. And I'll show you later that most of what I see are PC5. And I don't know if that's because of a instrumentation limitation that I have, or maybe it's just a characteristic of my latitude and the way that everything works. Now, when people have studied ULF waves over the years, they started to notice that there were certain frequencies that popped up regularly. And they called these, at first, these were called magic frequencies because they just popped up. And some of them are shown here on the left-hand side, 0.7 millihertz, 1.3, 1.9, and so on. So those were the frequencies that I was looking for in my observations, which I'll show you later. I did some Fourier transform or a fast Fourier transform analysis of my magnetograms, and I'll show you how my observations compare to that. Now, as far as instrumentation goes, I'm located at about 61 point something, maybe 62 degrees north magnetic latitude. And one of the characteristics of being at a higher latitude like this is that you have the auroral oval that can extend down or expand southward and bumps right up against Anchorage. And that would be during active magnetic conditions when the auroral oval reaches down into Anchorage or even overlaps it by a substantial amount in a strong storm. During quiet times, the auroral oval does not reach quite that far south, but you can see that it does cover a lot of Alaska under normal quiet conditions. Now, Anchorage is down here in the southern part of Alaska. And I also have an observatory up at Harp, which is right up here on the very edge of the quiet auroral oval. And so the Harp facility, and I just installed a magnetometer up there last fall. And so it's up there where the action is almost all the time, even during quiet conditions. Now, one of the things that I've learned from this study that I've been doing of ULF waves is that there's this concept called mapping of Lshells. And these are shells that are in increments of Earth's radius, 6,370 kilometers. And if you look at magnetic field lines that come that dive down around Anchorage, you'll find that the Lshell is about a 4.5 or so, shown up here in the upper right. And that works out to be, if you map that out into the magnetosphere, that works out to be to fall right in the radiation belts. And there's a lot of action going on out there all the time. And these radiation belts, shown by the red areas, are constantly expanding or contracting depending on magnetic conditions. So it turns out that Anchorage is, and my instrumentation is pretty well located for these kinds of observations. Now, I use the SAM3 magnetometer. It's a magnetometer that I've been working with since 2008. And I have mine set up for a 10-second sample period. And so the SAM3 consists of a controller shown here in the middle, and then 3 sensors. And the sensors are set up in a geographic reference system so that the X sensor is pointed north-south, and that's true north and true south. The Y sensor is east-west, and then the Z axis sensor is vertically. It's pointed toward the center of the Earth. And I run this 24/7, and it's connected to one of my technical PCs where I'm running the software for the SAM3, and I'm collecting data all the time, 24 hours a day, and that's what I've based this study on, is that data. Now, it takes more than just a magnetometer to make all this stuff work. You have to have some kind of a local area network. You need some timing supplies, an NTP, network time protocol server that keeps your PC clock running close to UTC. You have to have DC power supplies and so on. And of course, we don't have a lot of power outages, but every time you do, you lose data. So I run this off a UPS, an uninterruptible power system. Now, with a 10-second sample period, that works out that I'm sampling at a 10th hertz rate or 100 millihertz rate. And then if you work with that, you have the maximum frequency that you can get without aliasing is going to be 1/2 of that, or 50 millihertz. And that works out to be a 20-second period. And so that means that the frequencies that I'm looking at are less than 50 millihertz, or periods greater than 20 seconds. And so the possibilities for me with this instrumentation are PC3 through PC5, in other words, continuous pulsations classified as 3 through 5, or irregular pulsations classified as 1 and 2. And that, as I showed in that chart earlier. Okay, now let's get into some observations. These observations cover the time span shown on this solar sunspot cycle chart. And what I did is I went to the NASA website, or I'm sorry, the Space Weather Prediction Center website that has this a running chart, and I just zoomed in on the particular range that I was looking at. So 2008, which would be the beginning of solar cycle 24 through what was it, December of 2019 is when that cycle ended and the next one started. So I've got observations that cover this whole range here. And one of the concepts that falls out of this is that it doesn't matter what the local time is. What matters is the solar local time. And as you know, local time has these wacky time zones. For example, when the sun is highest in the sky at Anchorage, we're 2 hours off. Our local time is like 2 o'clock in the afternoon. So who wants to work with that nonsense? So all of my observations are looking at solar local time. And so in other words, the position of the sun in the sky. And these are related to Coordinated Universal Time, or UTC. And I've shown kind of a clock over here on the lower left that shows the day side of the Earth, the white area. And so when the sun is perfectly overhead, that is solar noon. And then we have solar dawn down here, and solar dusk, and solar midnight. And these correspond, solar noon is 2200 Coordinated Universal Time. So I use that then to correlate with the magnetograms that are in UTC. Now, here's one from December of 2010. I showed this magnetogram earlier in my presentation. So what I did is I broke that down into, first of all, here is where it falls on the time disk that I showed. So we're more or less in the dawn to noon sector here of the sun's position. And what I did is I grabbed just this short portion here from 1730 to 1810. So that would be this part of the magnetogram here. And I combined the X and Y observations or the data, and the X and Y, the vector sum of X and Y gives me the horizontal component of Earth's magnetic field, of the flux density. So this plot over here on the lower right then shows just that area zoomed in. And you can see there's periodic structures in here. And there's actually several types of, or several periods that pop out of that. And I did a lot of just hand counting of these periods here. And you can see that I came up with periods of 274 seconds for this period here, 384 for this period here, and so on. Definitely it's a periodic structure, but you can see that the periods actually vary from, say, 274 seconds all the way up to 609 seconds. Now, doing a Fourier transform of that time data then gives me this chart on the upper right. And I've listed the so-called magic frequencies here. And so you could compare those to what I'm seeing. Now, I've shown here at 0.4 hertz. That may or may not exist. That could just be a noise point. But these three spikes that you see here, those appear to be real frequencies. And I'm seeing them at 2.3 and 2.9. And so that more or less falls within the so-called magic frequencies that I mentioned earlier. Here's another observation from January of 2011. And what I've done is I've spliced two 24-hour magnetograms together. And you can see that we're going along here it's pretty quiet. And all of a sudden, the magnetic field takes a dive. Now, this is called I can't remember now. I just had a blank. But when you see a bay, it's called a bay. And when you see a bay like this, the first thing that you think of is that aurora. When you have a rapid change in the magnetic field, as shown here, toward the end of the first UTC day, that means the aurora is coming out. And if you're a radio amateur, you want to point your antenna north and see if you can contact other people whose antennas are pointed north, because you're going to get auroral radio reflections off of that. And so that's kind of a good indication. Well, getting back to ULF waves, one of the things that shows up with this magnetic bay is that it gets pretty noisy. And so those are ULF waves, and they cover quite a long time period here. Certainly more than 9 hours, maybe 11, almost 11 hours. And then there's another little episode here of pulsations that you can see over on the right, getting toward the end of the second UTC day. And what I did is I pulled out just a short part of this from 2100 to 2330. So that would be this noisy period right here. And just did a hand count of the periods that I saw and came up with 180 seconds. So those were PC5 type ULF waves that I got there. And since this whole chart covers such a long time period, you can see that they start in the dawn sector and actually move all the way over into the dusk sector. Now, here's another observation from 2011, this one in February. And again, I've spliced a couple days together here, and you can see a nice magnetic bay and some noisy periods that precede as well as follow the dive in the magnetic field. And so again, I pulled out a section of this from 0-100 to 0400 over here. That would be this area right here, and did a hand count of the periods and came up with approximately a 400-second period. So again, these are PC5 that you're seeing, and you know the sinusoidal nature of these ULF waves is really obvious from this chart here in the upper right, where I've zoomed in on the time. Another observation from 2014, and this one here shows a geomagnetic sudden impulse. So this would be the collision of a coronal mass ejection with Earth's magnetosphere, and it caused quite a strong deflection here in the neighborhood of maybe 70 nanotesla, which is extraordinarily strong deflection caused by a sudden impulse. And you can see that almost immediately following the sudden impulse, we started getting these noisy periods here, and then a magnetic bay. So a storm followed and into the next day there, but the ULF waves covered this region from approximately 1300 all the way up to 2100. So that was a good 8-hour session of ULF waves that appear to be instigated by this sudden impulse, or at least were related to the sudden impulse somehow. In 2015, I have, this would have been in December, I've spliced a couple magnetograms together. So these are two 24-hour magnetograms. And you can see that the period from roughly 1200 on the first day all the way to 1200 on the second day are pretty noisy. So those are, now a lot of these are longer period, high amplitude waves, and maybe not ULF waves by definition, but you can still see periodic structures in here that are really obvious. And so those may be caused by some other phenomena. For example, periodic density structures in the solar wind that are pulsing the magnetosphere and causing these periodic variations in the magnetogram on the ground. Here's one that covers over New Year's of 2015 to 2016. Again, it's two magnetograms, and you can see a nice magnetic bay over here on the left that was preceded by some ULF waves, and then it was followed by later on by more ULF waves over several hour periods. And so these covered quite a bit of the solar day shown here on this little plot up in the upper left-hand side. This is from 2017. ULF waves were produced in the late afternoon, evening of the UTC day. So this would have been around solar noon. My solar noon is 2000, so that would have been this time period in here. Now here's from 2017, and this one I broke out into different kind of analysis times. Now over here on the far left are some pulsations that you can see where I've zoomed in with this chart in the upper middle. And that shows basically one complete period, or maybe 2 complete periods of pulsations. And then I have another one here around 1500 of that day. And you can see that there are some periodic structures in here, some higher frequency than on the left, or I'm sorry, on the right, where this is a nice period here. And then around 1700 or so, you can see the waves that are plotted over here on the lower right-hand side. So this is from 1700 to 2000. And, you know, again, there's the periodic structures are really obvious. Now, if you take that and do some frequency analysis of it, then you come up with a plot that I've shown here. And again, I've listed the so-called magic frequencies just so they can be compared to what is being shown on my observations. And this 0.5 hertz that you see here shows up quite often. And that turns out to be what? Exactly 1/2 of my sample rate. So I'm not sure if that's instrumentation effect or if that's actually a real observation of the magnetic field frequency. Now, there are some other frequencies shown here, 1.7, 1.8, that falls within or nearby magic frequencies. 2.5, again, it's nearby, 2.9, 3.4, and so on. Now, when you get down here, you might be just looking at noise. I put some arrows here on these spikes, but they could very well just be background noise that's showing up as a particular frequency. In 2018, you see a nice rapid episode here of something. Now, I put a question mark here. I don't know if these are ULF waves, because when you plot, when you zoom in and plot, you have very sharp edges, which are not characteristic of the way the magnetic field changes. So this was in January of 2018. It could have been a road grader out there plowing snow. It could have been dump trucks hauling snow nearby my sensors. So I'm not sure if these are ULF waves or not, but it's easy to get fooled by local events, trucks and cars and what have you in the driveway that really aren't geomagnetic variations. Now, also in February of 2018, I did some analysis here of, here's a couple of magnetograms, and you can see that ULF waves span the UTC day or the end of one UTC day and extend into the next UTC day. So I've done some Fourier analysis of that. And again, I've listed the magic frequencies for comparison. And you can see that these are mostly low frequency in the 0.7 to 1.3 millihertz range. These follow basically in the same type of range, maybe up to 1.6 millihertz. So, but they definitely do, they're nearby these so-called magic frequencies. So it may be happenstance or it may be, real live solid data that we're looking at there. Here's 2019, where the ULF waves are really obvious. And you'll see that we're going along, it's pretty quiet, and then all of a sudden we get this buzz. And it lasts for, maybe 8 hours, almost 9 hours. And so those occurred in the noon to dusk sector of the solar day here at Anchorage. And there's another thing that kind of falls out of this chart like this, is that the ULF waves are much easier to recognize when the scale of the plot is low. Now, you see that the vertical scale on this magnetogram is plus and minus 60 nanotesla. So it's a very small range, and it makes these ULF waves really, really easy to spot. Now, if these magnetograms, the way I have my software set up is I have it set up for auto scale, so that if you get a magnetic bay or some type of a magnetic disturbance, it'll bounce that vertical scale up to say 1,000 nanotesla. So when you have ULF waves with an amplitude of maybe 5 or 6 nanotesla, that gets buried in the auto scale. So these are real easy to see when the scale is low. Here's an interesting event in 2020 when we had a sudden impulse, a 65 nanotesla, that again, another real strong sudden impulse caused by a CME colliding with Earth's magnetosphere. And you can see that ULF waves followed that event immediately, and lasted for a couple hours or so, and then things quieted down for the rest of the day. There's a lot more observations here. I'm going to skip that one. Let's take a look at August of 2022. And you can see that we have some ULF waves here in the first day shown on this 2-day magnetogram. And then we have some more associated with these magnetic bays on the second day. And you can see that these all took place in the dawn to noon sector of the solar day. And the frequencies that have popped out of this fall into the range of the so-called magic frequencies that I have listed in the upper right. And I've shown the zoom in of the magnetogram from 0 to 300, and the periodic structures are really obvious. Now, I took some of these Fourier transform plots that I made and showed kind of a histogram type arrangement here, just to see where my observations fell in with these magic frequencies that I mentioned. And you can see that there's some that show up a lot, and 0.5 hertz is one of them. And but there's over the 6 or 7 that are shown here, they don't all line up perfectly. And that may be an instrumentation problem. It may be an interpretation problem on my part of actually interpreting these ULF waves. It could be anything, but I did this just for fun. Now, most of my observations fell into the PC5 range. I did see a few irregular PI1 and PI2. Some of the ULF wave episodes lasted for several days in a row. So in other words, they weren't just something that popped up for an hour or two. They might go for 24 hours or more. Now, ULF waves seldom were seen during the solar midnight sector. So in other words, I didn't see hardly anything over here in this sector here. Almost everything that I saw were over in this side, on the day side of the daylight side of the solar day. Excuse me. Now, the fact that they were, what I was seeing was dawn to dusk on the daylight side kind of implies that they were the Kelvin-Helmholtz waves, the wind over water caused by the shear, hydromagnetic shear between the solar wind and the magnetopause. Some of the periods or pulsations that I saw have periods of maybe 30 minutes to a few hours. And I see those quite often at Anchorage. And these could be due to periodic density structures in the solar wind. And these are observed by NASA spacecraft. They're not observed on the ground. And but these are pulsations in the solar wind that pummel the magnetosphere all the time and maybe induce these ULF waves that I was observing. So that's pretty much the end of my presentation. I'm losing my voice, so I maybe it's a good thing I can shut up now, but I'll be glad to take some questions.
I have a question, Kent Gardner.
Yeah, Kent.
I built several Inspire receivers for lightning caused whistlers in the 5 to 15 kilohertz range. And when you take your technician ham license exam, they tell you that 30 kilohertz and above are RF and below are audio. Are these magic frequencies and stuff, do you classify them as RF, or are they mechanically transduced in your magnetometer?
Yeah, these are actually electromagnetic, so they are RF, but at extremely low frequencies. So you can't hear them. The only way I receive them are through the magnetic field that I'm sensing with my sensors. So it is definitely radio frequency or electromagnetic, certainly below the radio frequency band or even the audio band, but they are electromagnetic.